All right, so I had an issue with the internet recently this week, so I was unable to record the problems that I was working on for integration by parts. So you'll see them in Moodle as a separate document. I just wrote them all out by hand so you can see the answers. But today I'm able to get on the internet. So what I'm going to do is finish up chapter 5 with the last few examples of integration, use substitution, that is, and then we'll start chapter 6. Okay, so I'm hoping that all the internet issues are behind us so I can finish these up properly. So right now we're going to get back to 5D and look at a handful more of examples of integration with use substitution. So let's start with this case. We have a definite integral from 1 to 2 of e to the 1 over x power divided by x squared. Now, whenever you suspect that you might be able to use substitution, often it pays to algebraically rearrange the equation to see if maybe something suggests itself. Like here, for example, what you might want to think about doing is writing this as e to the x to the minus 1. And here, dividing by x squared is the same as multiplying by x to the minus 2 power dx. So how does that help us? Because if we try, for example, let's see, what can we do? Let's say that u is chosen to be x to the minus 1 power. Then du dx by the power rule for derivatives would be minus x to the minus 2 power. And then we could write this as du is minus x to the minus 2 power. Now we're in pretty good shape because you could see that we don't have the negative, but we do have the x to the minus 2 power. So if I rewrite this as minus the integral from 1 to 2 of e to the x to the minus 1 power times minus x to the minus 2 dx, that means what we have let me just rewrite that again, minus e to the x minus 1 power times minus x to the minus 2 power dx. So we can think of this now as e to the u du. Wow, that worked out rather well. That's pretty much the best case scenario because now it's very straightforward. And so we already know from past experience that the integral of e to the x dx is simply e to the x plus c. But here, this is a definite integral. We don't have to worry about the c. So instead, we have e to the u evaluated, negative e to the u evaluated from 1 up to 2. And since u was defined to be x to the minus 1 power, now we just plug in the two intervals, e to the 2 to the minus 1 minus e to the 1 to the minus 1 power. So e to the 2 to the minus 1 power is same thing as e to the 1/2 power. And then here, this is just e to the 1. And we could just basically leave it like that, or we could just simplify it a little. And we'll be left with minus e to the 1/2 plus e. And again, we don't need the constant because this is a definite integral. Okay. Oh, I see that. Yeah. And of course, if you want, you could rewrite this as minus radical e plus e. It's the same thing, of course. All right. That's good. So the tricky part was really rearranging the original expression in such a way that it's more obvious what would be a good candidate for u and du. And remember, when we're looking for du, we're okay as long as we have what we need, except possibly for a constant. We can supply a constant. That's it. We can't supply anything else. If we don't have what we need, we have to try something different. So here's another case that will end up being similar. In fact, very similar. So let's try this one. Why don't we write this as, first, I always like to move the constant outside the expression. It just seems like the constant is kind of a pain. It just is a distraction. Let's put it that way. Unless by coincidence, that's the constant we need to create du, but that's not likely. All right, so let's try this. U can be x to the minus 2 power. U dx, based on the power rule for derivatives, is minus 2x to the minus 3, or du is minus 2x to the minus 3 dx. And again, you can see we don't exactly have that. We're missing the minus 2, but that's all right. We can provide that by dividing by minus 1/2 on the outside of this expression. Just make sure that you have not done something that changes the value. In other words, I've multiplied the interior of this integral rather by -2, which means I must then multiply the outside by -1/2. And that's exactly what I've done. Okay, so that leaves us with, on the outside, we have -2. And then we have E. Now remember, we chose U to be x to the minus 2 power. So therefore, what we actually have here is e to the u du again. Okay. So we'll evaluate that from 1 to 2. Now we'll make the correct substitutions. So this is actually e to the 1/4. 2 to the minus 2 is 1 over 2 squared, which is 1/4. And then, of course, 1 raised to any power is just 1. So you ultimately end up with minus 2e to the 1/4 plus 2e. And that's it. We're done. Okay. Now, let's take a look at some more cases. This time we're looking at logarithms. And here's what we need to know. Some very basic rules that we'll need. First, the integral of 1 over x dx is the log of absolute x plus c. Secondly, and this is because of the chain rule, by the way, the integral of log x dx is x log x minus x plus c. And now, if instead of the natural log, we have the log base a, we have the same result, except that we have to divide by log a. Okay, this actually comes back to the idea that any log you have could be rewritten like this. Okay, this is an identity, and so that's essentially what's happening here. You're basically, you have to take into account when you have a log to some other base besides e, this piece here. Okay, that's where it's coming from. All right, but anyway, now, so what this means though is that when you see these in problems, you have to recognize them when you see them. So for example, this one, as soon as you see that the x is in the denominator, you have to wonder if this is maybe a logarithm. So why don't we try this? Let's let u equal x minus 10. Then du dx would simply be dx, or du, oh, sorry, no, it would be 1. Hold on 1 second. Yeah, that's better. So what do we have here? Let's move this 3 on the outside, as we always do, often do. Okay, so yeah, we were right. This is a logarithmic exponential. You can see because it is the equivalent. This one could have been written as integral dx over x. It means the same thing, of course. So what you actually have here is 3 log absolute value c, a u rather, plus c. Okay, and that's that. What about oh yeah, one thing we do have to pay attention to here, this actually technically we should specify that this result is true as long as x is not equal to 10. Okay, notice for any x other than 10, this function is, or this is the correct integral. Because if x equals 10, of course, we're integrating divided by 0. And furthermore, here you would have the log of 0, and that is undefined. Okay. What else do we have here? How about this one? Now, this one looks a lot like the last one. So let's try u equals x plus 2. So therefore, du dx would be 1. And therefore, du is dx. Oh, it couldn't be more simple. And again, for you would specify that this would be for all x under not equal to 2. Now, here's where it gets interesting. Sometimes we have a ratio in our integral, and sometimes there are techniques we can use to rearrange it to make it possible to use u substitution. Sometimes we need a different technique altogether, something you'll run into in Calc 2. All right, but for now, if you want to see if we can take one of these so-called rational functions, which simply means it's the ratio of 2 functions, and do whatever it takes to use u substitution. Now, here, what we'll probably want to do, let's try this. Let's rewrite it. So let's see, why don't we do this? Let's try u equals x to the 4th plus 3x squared du dx is 4x cubed plus 6x, or du is 4x cubed plus 6x dx. So it looks like we got lucky here, because this expression could be rewritten as, if we double this, then we'll have what we need. So let's try this. Let's multiply. Oh my God, what happened there? Okay. Let's multiply the outside by 1/2. Now, if I multiply the inside by 1/2, 2 times 2x cubed plus 3x equals 4x cubed plus 6x. So what I'm going to do is write this directly as 4x cubed plus 6x. knowing that 1/2 times all of this gives us back the original expression. And then I'll write this piece. And actually, let me rewrite it one more time. That way we can see very clearly that all of this is simply du. This is simply u to the -1. All right. And so therefore, what do we actually have? Let me just rewrite it one more time. 1/2 x to the 4th plus 3x squared to the -1, 4x cubed plus 6x dx. So this is 1/2 u to the -1 du, or 1/2 du over u, which clearly means we're looking at a logarithm here. And you recall that u was chosen to be x to the 4th plus 3x squared. And then, of course, we can't forget the c. And that should do it. Now, this one is, yeah, let's go back and grab that special rule. Yeah, it's obviously this one. Whoops. Let's see, where was I? Oh, well, then, this is, it's already in the right form. It's just that a is 2. That's the only thing we have to note here. So we'll end up with x over log 2 ln x minus 1 plus c. So you know what I'd like to do? Let me just quickly show you an alternative way we could have done this. So I mentioned earlier that the log to base 2 of x is equivalent to natural log of x over natural log of 2. But natural log of 2 is a constant. So I'm rewriting log 2x like this. Then I'm going to move this on the outside. Now, the integral of just log x, let me just remind you what the rule looks like for that one. Okay. So we'll bring that back. So what this is implying is that this one is the equivalent of 1/2, or sorry, 1 over log 2. And then we'd have all of this, x ln x minus x. We could put the c outside. It doesn't really matter where the c goes. It's a constant. So when we wrote our answer up here, we factored, this is the answer we got here. So what happened here is that we factored out in x. So in other words, you could rewrite this as 1 over log 2 there's an x in both of these terms. So I'm going to factor it out, and it becomes log x minus 1. And now you'll see that it's identical to what we got when we used the rule directly. X over log 2 times log x minus 1, all plus c. So basically what you're seeing here is the rationale behind this rule. We don't technically need a separate rule for the second and the third cases. But it's nice to have it. It's just that you can see one is the second, this one down here is simply, I guess you could think of as a special case of this one. But the key is right there, right? This definition right here. And by the way, I want something interesting about that. The reason why I checked this out one day, the reason why this is so important is because if you look at any calculator like the TI-84 series, what you'll notice is that there's a button for log, natural log, and there's a button for log 10, and that's it. There aren't any others. There's no log 2, log 3, log 4, and that's because they're not needed. You can recreate any of those with this identity right here. In fact, even the log 10 is redundant, but it's a very popular one. So, the calculator, they're trying to find the functions that everyone is happy with. Just like the tangent button is redundant because the tangent is simply the ratio of the sine of the cosine. but they put it there anyway because people want it there. Oh, there's a lot of redundant buttons on a calculator, but whatever. It's there's only so much room on there. All right. So what other examples do? Oh, here we go. We couldn't avoid trig functions forever. So, all right. Now, here's what I want to remind you. Now, you know that in the back of this book, there's a couple of charts with integrals and derivatives. So I'll quickly remind you here that oops. And so this implies that the integral of sine x dx is the negative cosine. Okay. And that also implies that the integral of cosine x is the sine. So that means we have to think about what to do about u. If I let u be a function of the cosine, that should work because when I take the derivative, the du dx, I'll end up with negative sine x. And I don't have that, but I can produce it by putting negative here and a negative here. And so that means I'm going to have du in the numerator. Well, that couldn't have been much more simple. Let me clean it up a little. Okay, well, we know where this is going. It's going to be a log, a definite integral. Actually, let me move the negative outside there. And remember, u is 1 plus cosine x. So I'm making the substitutions. Oh, actually, wait a minute. Wait. Yeah, no, that's right. This is supposed to be zero. That's why this is zero. Yeah, that's right. Okay, now if you want, you can take out your calculator and look these up if you don't have them memorized, which I don't. Yeah, for certain disciplines, trig functions show up all the time. Not so much in economics and finance. So I don't have these memorized. The cosine of pi over 2. Don't forget, when you're using this calculator, if you're going to be using pi, it thinks you're dealing with radians. Make sure you're in the radians mode. Actually, there is something I stumbled across this week. Maybe let me do this with you. Let's see if I can find this. If you go to this website, ti89.com, online calculators, ti84 online PHP, which I can send you a copy of this if you want it. You'll notice that if you scroll down here, it has all kinds of fun stuff, but what you're looking for is, oh, it's way down here, testnav.com. And if you click on this little button, this little icon, this is a virtual TI-84CE. Now, as far as I can see, so far, I've only been using it for a few days now. It appears to me that it's identical to the real one, the one you have in your hands. So I'm going to confirm that. At the top, if you go to mode, wow, it does look good. You see it right here, it says radian. If you leave it there, I need to know the cosine of pi over 2. The pi button is, I find it easier to find things with the real calculator. The pi, oh, here it is. It's the second button here of the exponentiation key. Divided by 2, close, enter. 0. All right. So let's fill that one in. Okay, so not negative log 1 plus 0 minus log. So the cosine of 0 would be, by the way, I do want to point out, if you don't use this for a few minutes, sometimes it disappears. You may have to go back and reinstall it. 1. Okay, good. Oh, I just realized I've already plugged in the 0 and the pi. These shouldn't be here. Okay. Anyway. Oh, no, sorry. This is just, it's just 1. Cosine of 1. All right, now, finally, we get all that straightened out. It should be the minus of, in the first case, we have the log of 1. And then when I distribute the negative across here, I'll have plus log of 2. Log of 1 is just 0. So I'm just going to end up with log 2, natural log 2. Okay, very good. So, yeah, here I had no idea. Somebody actually showed it to me, and I realized that this could be very helpful because obviously you can really see what I'm doing, as opposed to normally when I just, try to hold it up to the window, which doesn't help a whole lot. You don't really need this unless you want to fool around with it. But you can see why it would be so helpful to have this available for classes like this. So anyway, but I'll send you, I wrote out the instructions for this. I'll post them on Moodle later on after we're done. If you're interested in using this thing. Okay, now, oh boy. Integrals of the inverse trig functions. Yeah, like the arc sine, for example. So you might recall what that means. If, for example, the sine of, let's say, 90, and just double check this. Oh, I might as well do it while I have this wonderful tool in front of me. I'm going to go back to the mode and switch to degrees. And then I'm going to ask it for the sine of 90. It's 1. Okay, so if the sine of 90 is 1, that implies that the arc sine of 1 is 90. All right, so the arc sine is it's an inverse, okay, and that's why the notation is written like that. You know that x to the minus 1 is 1 over x. Sine minus 1 is arc sine. Okay. So it turns out, if you look at that formula or that table, in fact, why don't I get the book open real fast? And let's take a look at this. You'll find several of these in that integration chart. Oh, it's way at the end. I better not guess. There it is. Now 763 is the page number. As far the PDF page is probably a little higher than that. Let me guess 770. I don't know why they're not identical to each other. They just are. Oh, here we are. I got pretty close. So what the ones I'm specifically referring to would be these three actually. We've got this form, the integral of du over the radical a squared minus u squared is the arc sine of u over absolute a plus c, then a squared plus u squared in the denominator gives us an arctan. And then something like this gives us an arc secant. So you'll see these scattered throughout. Here they are. Oh, they're down here all together. Numbers 15, 16, and 17 are the arc trig functions. So what that means is that if you see, and by the way, a is a constant in each of these cases, u is the variable, which the reason why they're using u here is because they just want to make it clear that u could represent any function of x that we choose, but the a is a constant. So it's just up to us to recognize these when we see them. So like here's one. Now, as soon as you start seeing square roots in the denominator and squares like this, your first instinct should be, is this one of those special integrals that involves arc sines or whatever the case may be? So let's see if it's this one. If you try to do u substitution the way it is, you can see it's not going to work because you're going to end up with u is 1 minus x squared. And that's fine, but what about your du? You don't have the negative 2x, and you can't just provide it yourself. The only thing you can provide is a constant. So that would be a signal that you need to do something different. So instead, we look at the chart and we say, hey, wait a minute, that looks awfully familiar. Why, that looks just like this arc sine function, where a is 1, so that a squared is 1. U is x, which means that minus u squared is minus x squared. Du is dx. So we've got du over radical a squared minus u squared. So that means it's arc sine u over absolute a plus c, arc sine x over absolute 1. So since it's 1, we can just drop it out. It's the arc sine of x plus c. Man, that one would take some serious practice to recognize that one. But once you get used to it, you'll start to see the patterns there. Like if you look at these, well, okay, I shouldn't say they look different. You look at them and say, I wonder. And if you're wrong, you're wrong. You can try something else. I don't see any of the others that look quite like that. So this is really kind of an art form, identifying the correct form for an integral. Well, that was easy. Oh, I just realized, you know what? I was so excited to show it to you. I forgot that this is a definite integral. So we still have to evaluate it. Oops. All right. Let's get rid of that C. Yeah, that was kind of important. All right. So we still have one more step. So once again, it's the arc sine from 0 to a half. Now, I think your calculator does have an arc sine function in it. Let's go find out. Let's go look at our simulated calculator. Let's see, where do you suppose they are? There they are. I can see them. You see directly above the sine, cosine, and tangent are the equivalent corresponding arc functions. So first things first, let's get ourselves back into degrees mode. Oh, there it is. Oh, we are in degrees mode. Okay. So the arc sine of a half. Oh, no, that's not right. It has to be the second. That's better. Oh, whoops. Yeah, you got it. Don't forget, you're actually not using the actual calculator. If you try to type on your computer, sometimes it works and sometimes it doesn't with this thing. All right, so that's 30 degrees. By the way, you don't have to turn it into degrees. And the sine, arc sine of 0 is 0. So you could think of that as 30 degrees. But if you'd left it as radians, I don't know if that would have made any real difference. Nah, let's just do it like this. It should be fine because no, what the heck? Let's find out what it would have looked like with radians. I mean, we know that 180 degrees is pi radians. So that, whoops. In other words, we don't really need to go back to the calculator because um, pi radians is 180 degrees, which means that pi over 6 radians is 30 degrees. So you could do it directly. But I think if we do it in the calculator, I'm kind of wondering how it's going to handle this. I'm going to go back and ask it for the arc sine of a half when it's in radians mode. See, now that's the thing. Yeah, it's got 0.5233. If I multiply that by 6, it should come back to pi. Yeah. Um, I don't know if there's any way that we can force the calculator to take like 0.52355 and show it instead as pi over 6. Actually, I think there is a way. I just don't know what it is. I'll check into it. But yes, that's what that is meant to that is pi over 6 is 0.5 something. All right, now what about this one? Now what we do is we look at the chart. This appears to be in the form oh if A is 2 and U is 3x, then we're all set. Okay, because of course then A squared is 4 and U squared would be 9x squared. So let's see if that's on our list. Why, there it is right there. It's the arc sine again. Okay. Okay. So this time it's an indefinite integral, so we don't have to worry about evaluating it. And that would be it. That's the whole thing. Ooh, not bad. Not hard. But again, it's all about recognizing this form. Oh, gee, you know what I just realized? I goofed. You know why? I was so eager to, again, I'd forgot about one little detail. Oh my God. Because we don't have what we need. I what we should, I just realized now. Let's go back real fast. I just realized I goofed it up. Sorry. Hold on. We're missing something important here. Um, we're going to need du in the numerator, not dx. I did not copy this correctly. That's where I went wrong. This should have said du. Okay, notice this is the original question, but the formulas they're giving us are written like this: du, integral du over square root of a squared minus u squared. And we don't have that. Here's why. Because if u is 3x, then du is actually 3dx. So we need to provide the 3 here. Then we can carry on with the rule. So let's write it like this. Okay, so then it becomes 1/3 du over radical a squared minus u squared. Now we're all set. Okay. And let's see, I do not have enough room for this. Hold on. Okay. So now it's fine. Okay, very good. Beautiful. So yes, I goofed on the u part. Du, yes, we needed the du, and so we needed to provide ourselves with a constant. So it's 1/3 sine 3x over absolute 2, and we can ditch the absolute 2. You can leave it there or get rid of it. Clearly, the absolute value of 2 is just 2. All right. Let's see. It looks like we got one more here. Let's see if we recognize this form. So let's look at the ones that we have to choose from. This is the sum of squares, so it looks like it might be that second one right here. Integral of du gives us 1 over a arctan u over a plus c. That's it. No absolute values. So let's try u equals 2x. Du dx is 2. Du is 2dx. And a would be the 1. So that a squared is 1. So do we have what we need, which is du? Well, we're missing the 2. If we want this to be du over a squared plus u squared. So we'll provide the 2 here. And we'll multiply the outside by 1/2. So that's going to be, yeah, now we got du over a squared plus u squared. So we have a half. We still need 1 over a, but a is 1. So we're actually just going to wind up with the arctan of 2x plus c. We don't need to divide by the a because it's just 1. Okay. All right. So by now, I think we're experts in u substitution, although what changed here was that we're applying it to functions that are not just straight ahead polynomials, which we were doing earlier. We had to now deal with exponential functions, we had to deal with logarithmic functions, and we had to deal with ratios, and we now had to deal with arc trig functions. All right, so what comes next? Well, this is it for chapter 5. That's that. So what I'd like to do is get started in chapter 6. which is, by the way, the last chapter of the course, which it's sad, but it means that you're ready for Cal 2 is what it means. So this is called applications of integration. Okay. So, of course, integration can be used for many different kinds of applications. Certain quantitative disciplines lend themselves very well to this kind of thing, such as physics, finance, economics. Some disciplines are more based on what we call discrete math. This is continuous math. Discrete math means you're dealing with finite sets. Computer science tends to be more focused on discrete math. But the two of them complement each other very, very well. But this is where we tend to see a lot of physics. In fact, Newton invented physics so that he could describe better the laws of motion that he invented. Yeah, Newton, imagine yourself, you're one of the greatest thinkers who've ever lived, and you say to yourself, nobody quite got around to inventing a branch of math that explains what I'm doing in physics. I'll tell you what, I'll do it myself. I'll just make up a whole new branch, and that will be the end of it. That's a nice position to be in. So anyway, now it turns out the log of a function can be expressed in terms of integrals based on the first fundamental theorem of calculus. And so you recall, this is the statement of the first part of the fundamental theorem of calculus. Now we're going to see what we're going to do with it. Okay, what is it for? So the natural log of x actually is formally defined as the integral from 1 to x of 1 over t dt, which shouldn't be surprising to you because we know that the integral of 1 over t dt would just be the natural log. But what's happening here is that the integral itself ranges from 1 to x. It has to start at 1. Remember, the natural or the log, any log of 0 is undefined. Any log of any value under 1 is going to be negative. So graphically, this is what we're actually seeing. So now what they're doing is they're making a distinction between two cases. X is greater than 1. Let me label that a little better. Okay, they don't actually show you x equals 1 exactly because that's just 0. So anyway, when x is strictly positive like this, it can be interpreted as the area under this curve 1 over t over the range that we are integrating it. Over here, it's the negative. Now you notice this area itself is positive, but we multiply that by -1. So whatever this is, let's say it's 3, then the negative of that is the natural log in that range. This is how it's formally defined. Now, we know some of the key properties. We've already taken its derivative. The derivative of log x is simply 1 over x. We also recall from the chain rule, this becomes g prime of x over g of x. This would be for any function of x other than x itself. And of course, this is only true if x is strictly greater than 0, because the natural log of 0 itself is undefined. That's because there's no value whose exponent will bring us to 0. Okay, the integral then of 1 over u du is log u over plus c. And furthermore, we had all these wonderful properties. The natural log of 1 is just 0 because 0 to the 1 is 1. Or not 0, hold on. Because e to the 0 power is 1. Okay. The natural log of a product is the sum of the individual natural logs. The natural log of a ratio is equal to the difference. And then finally, the log of a to some exponent r is equal to r log a. All right, so here, oh yeah, this is what I was just saying. This is the derivative of log g of x. Okay, so let's do this. So if we have, oh, the original function was, so if we allow g of x to be the 5x cubed minus 2, based on the power rule, a g prime of x would be simply 15x squared. So the ratio of those two would be 15x squared over 5x cubed minus 2 due to the chain rule.